In today's video, we're going to be talking about radioactive decay. After watching this video, you should be able to describe the types of particles that will be emitted during a radioactive decay, and then be able to complete some decay equations. In general, we're going to keep this stuff relatively basic, just so you have some general idea of what happens during radioactive decay. So let's do a quick review of what we've kind of discussed thus far. Protons and neutrons can be found in the nucleus. Protons have a positive charge and neutrons have no charge. And that's really what we focus on when we talk about radioactive decay and all that good stuff is the charge and that exchange of charge. And then, of course, electrons can be found outside the nucleus, orbiting around that central nucleus. And sometimes protons are referred to as plus 1e or plus 1 elementary charge, which if you remember back from static electricity, 1 elementary charge is this in coulombs, this really small number. And then electrons are sometimes referred to as minus 1e, minus 1 elementary charge. Now, in the previous lesson, we were really concerned about the various masses of protons, neutrons, and electrons. We got real particular about it. In this lesson, if it makes you feel better, we don't care quite as much about particular masses. So we're going to actually go back to, again, assuming protons and neutrons are about equal in their mass, and one proton or one neutron is typically referred to as 1U, or 1 atomic mass unit. An electron is about 1,800 times smaller than a proton, so in most of these problems we're going to assume electrons are massless. Now if you go back to the previous lesson in nuclear physics, that was not the case. So I'm sorry we kind of flip-flop here between caring about mass and then not caring about mass as much, but that's just kind of how the cookie crumbles. Now what gets a little weird when we talk about nuclear physics is how we describe nuclei. So here is a helium atom, and down here is the atomic number, and up here is the atomic mass. And basically this bottom number is going to be the charge in the nucleus. And in this case, helium has a plus 2 charge because helium has 2 protons in the nucleus, and they have a plus 2 charge. This top number is the atomic mass, or the mass number, and basically that gives you the number of protons plus the number of neutrons. So in this case, we know helium has 2 protons, and since its atomic mass number is 4, we can take 4 minus 2 to figure out that this baby has also then 2 neutrons. Okay, so this is just kind of like a general template of how it's laid out in physics, and I realize this, I believe, is backwards compared to what you learned in chemistry, but again, this is kind of how it is in nuclear physics. Okay, let's do a quick example here. Here is a hydrogen. I notice it has an atomic number of 1 and an atomic mass of 1. The question is, how many neutrons does the above hydrogen have? All right, well, the way to figure out how many neutrons an atom has is to take this top number and subtract it from the bottom number. So what is 1 minus 1? Well, that is 0. Yeah, so this baby has 0 neutrons. Another question I could ask you is, let's say I have an element with an atomic number of 1 and an atomic mass of 2. What element am I? Well, this bottom number, the atomic number, is actually going to determine the element you have, because that's going to determine the number of protons you have. Protons actually determine what element you are talking about. So if you look at element number 1 on the periodic table, you would find that this is hydrogen. All right. So hopefully that's not too horrible thus far, but that's kind of a general gist of what we're going to be talking about. All right, well, we've been discussing this thing called subatomic particles. Those are protons, neutrons, and electrons. If we were to use this kind of numbering scheme for a proton or a neutron or an electron, what would that look like? A proton would have a plus 1 charge, which here it is right there, and it would have a mass of 1. Okay, so a proton would have a plus 1 charge and have a mass of 1. Notice a neutron has no charge. Okay, so it'd be 0 here, but does a neutron have mass? Absolutely, so we can put a 1 there. So notice it's kind of funky that there's a 0 down here, but that is the case. If you were to use this describing nuclei method for subatomic particles, you would be using 0 for neutrons as the atomic, or this number down here in the bottom left, and then this number here in the top left would be the mass. What would an electron look like? That's a great question. An electron would have no mass. Okay, so notice this is 0 up here. And what charge does an electron have? It has a -1 charge. And the symbol for an electron is typically an E. So kind of weird to see it like this, but this is how they kind of do things with nuclear physics. So there are 3 particles that you need to be familiar with in terms of radioactive decay. These are 3 things that kind of can get shot off by an unstable atom that's undergoing radioactive decay. The first particle is an alpha particle, and an alpha particle is simply a helium nucleus. What is found in a helium nucleus? A helium nucleus will have 2 protons and 2 neutrons. Okay, so 2 protons and 2 neutrons shoot off when you have an alpha particle released. The symbol for an alpha particle is this kind of, it's a symbol alpha, but to me it looks kind of like a little fish or a goldfish or something like that. And notice it has a charge of +2, that's this bottom number here, and then it has an atomic mass of 4, so that means that it has 2 protons and 2 neutrons are being released. So that's an alpha particle. A beta particle is simply an electron. Okay, it's an electron being released. So if you have a beta particle released during a radioactive decay, basically an electron has been released, and we talked about the symbols for electrons. An electron has a charge of -1. It has no mass. And so here it is. This is the symbol for beta, and here it is, -1 and 0. We won't really get into this too much, but there's this thing called antimatter. And antimatter is basically matter, but it's not matter, it's antimatter. It has the same mass, but opposite charge. So the antimatter to an electron is something called a positron, and basically all it is a positively charged particle. And you still use the same symbol beta, but instead of -1 here, it'd be +1. Okay? We don't really deal with it too much, but just be aware there is this thing called antimatter, and basically it's the opposite charge of the matter that we know and love so dearly. The last type of particle you need to be aware of is a gamma particle, and a gamma particle is just a high-frequency photon. It's basically energy that's being released. And so it has 0 mass and 0 charge. It's just a bunch of energy, and so this is the symbol for gamma, and notice everything is 0 across the board, just because it's energy. It has no mass, it has no charge. It's just energy that's being released. Okay? Kind of a refresher from previous lessons, we talked a little bit about what radioactivity is. Basically, a radioactive material is something that has an unstable nucleus. That strong force isn't able to hold that nucleus together, and the electrostatic force is starting to take over and it's starting to punch things out. It's starting to shoot things out of the nucleus. Whether it's an alpha particle, a beta particle, or a gamma particle, things are being shot out of that nucleus. And those particles can be very dangerous because it can be dangerous to humans or other animals or things that have tissue, basically because when those particles hit our tissue, they can mess up our DNA, and it really gets into a whole other ball of wax. It'd be interesting to talk about. It's just beyond the scope of probably this lesson today. But just be aware that radioactivity basically is the nucleus is unstable. Things are being punched out of that nucleus because the strong force is losing the battle to the electrostatic force, and those particles can be dangerous to humans or other animals. If we talk about the type of reaction that would occur if you were to set up, say, an equation, this is kind of what it would look like. An alpha decay is simply where the nucleus is going to lose an alpha particle. So they've kind of got this interesting naming of stuff. This X here, that is the parent nucleus. That's what it starts off as. Okay, and notice here's Z and here's A, and these are just arbitrary letters that we're using to kind of represent the atomic number and the atomic mass. I'm not actually giving you real elements here, it's just made up stuff. So I have this parent nucleus sitting here, and it's going to undergo an alpha decay. Okay, so here's my alpha particle. And what is it left with? Well, what is left with is called the daughter nucleus, which is represented by the letter Y here. And basically what ends up happening is this conservation has to occur here. So if it just lost a charge of +2 and a mass of 4, notice my Z now is going to be -2, okay, because it lost 2 positively charged particles, so the charge on the nucleus is going to drop by 2, and the mass of this whole thing is going to drop by 4. Okay, so notice if I add this up, a minus 4 plus 4, it equals a, and z minus 2 plus 2 equals z. Now this is a little confusing, so take some time to either pause the video or mull over it a little bit, but basically you have to make this balance. This math equation here must balance. And that's really the challenge of this lesson is, can you do this? And if you can do this, this will be easy peasy. All right, let's do another example of a different particle. Let's do a beta decay. Remember, a beta decay is basically an electron that's being released. And so here on the left, I have my parent nucleus and then A and Z. And notice we have a beta particle that's been released. A beta particle has a -1 charge and 0 mass. So notice A is just A. Okay, nothing happened to the mass. Okay, it's just A. But Z now is Z plus 1. How come? It lost one negatively charged particle, so the overall charge of that system is going to be plus 1. So Z is 1 bigger. And the way to check your work is, does Z plus 1 minus 1 equal Z? And the answer is yes, it does. Does A plus 0 equal A? Yes, it does. Okay, so just if you need to take a moment to check yourself and see if that all makes sense, when you're doing problems or what have you, that's not a bad way to check your work. If this right side doesn't add up to the left side of the equation, and this arrow I kind of look at as almost like an equal sign, if you will, then something's not right. Let's take a look at an example with some antimatter. Now you won't see this too much, but this is just kind of for fun. If you were to have a positron emitted, what does that look like? Well, here's our parent nucleus, A and Z. A positron is just a positively charged electron, if you will. It's the opposite of an electron, the charge that is. So all that happens is A stays A because a positron has no mass, but instead the overall charge of the nucleus has dropped by 1. How come? It lost a positively charged particle. And just check your work. Z minus 1 plus 1 equals Z. A plus 0 equals A. That looks good to me. Okay, so things seem to be working in that way. The last type of decay that I'd like to show you is a gamma decay. And a gamma decay, remember, is just a high-frequency photon. It's basically energy that's being released from the nucleus. And this is probably the easiest of the equations to balance. Because basically, what ends up happening is your parent nucleus gets a little asterisk next to it. And that asterisk basically just shows that parent nucleus is in the excited state. And it's just raring to go to give off some energy. Okay, so then it undergoes gamma decay. Here's my gamma particle. It flies off. And what are you left with? Well, you're left with the daughter nucleus of A and Z. Now notice it is no longer excited. That asterisk isn't there. Energy has been released in the form of light or what have you. Okay? That takes care of this video. I will see you guys next time.